Okay, we had a technical glitch here, so it got broken up into a second file. So we'll pick back up where we were. Our second force was an electromagnetic force, and it, like gravity, can operate at a pretty long distance, but the electromagnetic force is a whole lot stronger than our gravitational force. This electromagnetic force, in fact, holds together the atom. It's what causes the electron to be attracted to the proton, to keep it in the orbit here. And when we have chemical reactions, it's these charges that cause our chemical reactions. So anything that's not a single element makes use of the electrostatic forces, and it's pretty much what holds together solid things in our world. Okay, our buildings, our towers, the trees, all are held together by this electromagnetic force. Now there are two more forces that act that we know of. One is called the strong nuclear force, but it's very short ranged. It doesn't act over a very long distance. As a matter of fact, it's just the nucleus, within the nucleus of the atom. And then we have a weak nuclear force. Again, it's very short range. And they only operate within the nucleus of the atom. So let's go back to our model of an atom. We said inside the atom we've got protons. We can also have some neutrons in the nucleus. Neutrons are very similar in size to a proton, but the big difference is they are not made up, or they do not have a charge. And then orbiting around the atom, we've got electrons. So one of the things that might have occurred to you is if like charges repel, why is it that we have, and our electromagnetic force is so strong, why is it that we have more than one proton in the nucleus? Okay, because if they're so strong, the closer that we get together, right here, or that they get together, the stronger that force is. They should not be able to come close together. Well, that would be true, and the electromagnetic force does indeed operate on them, trying to push them apart. But our strong nuclear force is even stronger than our electromagnetic force. It just operates on a really short range within the nucleus of an atom. So within the nucleus of the atom, we've got two forces. Our nuclear strong force pulling together, and then our electromagnetic force, which is pushing them apart. As long as they're really close together, the strong nuclear force wins, and the nucleus stays together. Now, if we happen to have a really big atom, such as maybe uranium, plutonium, something like that, you can see as it gets more neutrons, more protons, this atom is getting bigger and bigger and bigger. Okay. If we continued like this, eventually we get so big that the strong nuclear force, its range doesn't include the whole nucleus. Its range might only include part of the nucleus. In which case, sometimes this atom splits up into two. And that's what we call nuclear radiation. In materials that are radioactive, they're called radioactive because sometimes they split up like this, and this nucleus gets fired out, sometimes with a lot of speed, because our electromagnetic force is very strong. So it hurls the nucleus out, and if it hits our bodies, it can actually damage the cells in there. So that's what nuclear radiation is, and why it happens. It's because our electromagnetic force is so strong. Normally we've got the nuclear strong force that holds it together, but it's very short range force, and so once it gets outside of that range, then the electromagnetic force becomes stronger and pushes them apart and basically throws the nucleus at us. So we've got an equation here for our electromagnetic force. So let's work through an example with it. Let's say we have two charges. One of our charges is positive, and one of our charges is negative. Our positive charge will be 3.0 times 10 to the negative 6th coulombs. You may also see this written sometimes as 3 microcoulombs. This is the Greek symbol mu, just like we used for friction. In this case, though, it means 10 to the minus 6th. Our negative charge will have a value of negative 2.0 times 10 to the negative 6 coulombs, or negative 2 microcoulombs. And these charges are separated by a distance of half a meter. And we want to find the size of our F. Find F. Well, we have F equals K Q1 Q2 over D squared. So 9 times 10 to the 9th Newton meter squared per coulomb squared. 3.0 times 10 to the minus 6 coulombs, and negative 2.0 times 10 to the negative 6 coulombs, divided by 0.5 meters squared. Okay, once again, you're going to want to be careful about how you put this into a calculator. You're going to want to do the 9-second, and then the comma, right above the comma is the e to the 9th, times 3-second e to the negative 6th, times negative 2-second e to the negative 6th, divided by 0.5 and squared. Again, don't forget that you have to square the distance between the two charges. And when you put in enter, you should get a negative 2.16 newtons. Or 0.216 newtons, sorry. Okay, so very similar to the calculations that you were doing when we were doing gravity. Not much different than those, just the fact that now we have charges. Since we've got charges, we've got one positive, one negative. We got a negative value for the force, and so that means that it's an attractive force. It's attracting them together. We didn't worry about it so much when we were talking about gravity, because gravity, the masses always attract. There's no negative masses. Okay. So far, this shouldn't have been too much of a problem. Like I said, very similar to what we did before. But one thing that we have to be careful of with charges is we often have more than one charge. Since we often have more than one charge, we end up having to do more than one calculation to find the net force on it. So let's look at a problem here. You have three charges arranged as shown. We're going to have a negative charge on this side with a value of negative 3.1 microcoulombs. So this is charge 1. Charge 2 is also going to be negative. It'll be a negative 1.5 microcoulombs. The distance between these charges will be 0.13 meters. And at the end of this line, we'll have a positive charge of plus 2.6 microcoulombs. And this is charge 3. And what we want to do is find the force on charge 2. Okay. Well, here we've got more than one forces that are acting, so we do need to be careful. From charge 1, these two forces are the same, so we'll have a repelling force. From charge 1 on charge 2. Okay. Although it's not showing up real clear, let me zoom in real quick. The way we're going to write this is force from due to charge 1 on charge 2. But charge 3 is the opposite charge. So if we're looking at charge 2, on charge 2 we additionally have a force going this way, and I just wrote this wrong, due to charge 3 on charge 2. Okay. So charge 2 has two forces acting on it. One, a repelling force from 1, and an attractive force from charge 3. So we're going to have to determine the value of both of these forces. So let's start with the force of 1 on 2. And it's 9 times 10 to the 9th Newton meter squared per coulomb squared times negative 3.1 times 10 to the negative 6 coulombs times negative 1.5 times 10 to the minus 6 coulombs. And this is divided by 0.13 meters squared, because that was our distance from our charge. So now we put these into the calculator. Go ahead and do that at this time. what you should have gotten is a force of 2.48 newtons. So now let's look at the force on charge, or due to charge 3 on charge 2. That's K Q3 Q2 over D squared. So that equals 9 times 10 to the 9th Newton meter squared per coulomb squared times plus 2.6 times 10 to the negative 6 coulombs times negative 3.1 times 10 to the negative 6 coulombs and I didn't put the distance here. The distance between charge 2 and charge 3 will be 0.21 meters. So when we put on our distance here, 0.21 meters squared, so calculate our force due to charge 3 on charge 2. And what you should have gotten is a negative 0.80 newtons. Okay. Now we come to something where you have to be real careful about with electrostatics. Our force here was a negative 0.80 newtons. That means that it is an attractive force. The two charges are attracting each other. So that means that the force is going to the right, because there we were talking about between charge 2 and charge 3. For F12, our force was positive. Getting a positive force in this equation means that the charges repel. In other words, these two are repelling. This one is trying to push the one in the center to the right, away from it. Notice the positive and negative for the forces did not mean they were both going in the positive direction. You've got to be real careful about that. What the negative means when we put it into this equation is whether they're attractive or repelling. It does not mean the direction that they're going in terms of the positive x direction or the negative x direction. You've got to put it in a free body diagram and then decide what your net force would be. In this particular case, our net force, our sum of the forces, is going to be equal to F12 plus F32. And we're talking about the size of the force now. So we've got absolute values here. The size of the force is added together. We don't care whether our equation came up with a positive or negative. We're going to add the positive value. So the sum of our forces is equal to 2.48 newtons plus 0.8 newtons so our force is 3.28 newtons in our positive direction, which is to the right. Again, be very careful about that with electrostatics. When you put it into the equation, the negative sign and the positive sign does not tell you that they're going in the positive or negative direction. It just tells you whether they're attracting or repelling. You need to take that information, put it into your free body diagram, and then from your free body diagram, decide which forces are in the positive direction and which are in the negative direction. Okay? And we're going to stop here for today.